Yeah, it's really an honor and a pleasure to be here, especially because at this program there's lots of old friends, people I haven't seen for quite a long time. It's just great to see them again. Okay, so this is a topic that I don't know if it's the usual kind of thing I work on, but Henry Cohn came to So a guy named Henry Cohn came to Brown about 7 years ago, and he gave a lecture on all of his beautiful results about energy minimization. And then he kind of mentioned there was this sort of, in a sense, notorious or embarrassing kind of unsolved problem. And I remember being shocked that they knew all this really fancy stuff, but not this kind of simple thing. So I got interested in this, and I solved the case of it, and then after about 7 years, I finally, in a sense, well, it's maybe solved the main point of it. So I'm going to tell you about this problem. I thought I would start with something that's completely trivial, maybe the easiest theorem that's ever been presented in a lecture like this. But anyway, so the theorem is that on the real numbers, x squared minus 2x plus 1 is greater than or equal to 0. Okay, so just so I'm not insane, let me show you the first proof. It equals x minus 1 squared, and the square of a number is non-negative. But then there's a second proof, which has 3 steps, which is maybe not a good sign. So the first step is you reduce to a compact domain. What I'm saying is that, like if x is bigger than 8 or smaller than minus 8, then, the first term, x squared, is so large that obviously this thing is positive, no matter what you do for the rest. Then the second step is that you would eliminate most of what's left with just explicit computations. So on the left and the right, in a way, I've shown 2 different computational schemes. Like one is you just take about 1 billion evenly spaced points, and you compute that, like between minus 8 and 63 over 64, the thing is, at these points, the thing is very positive. And then you might say, well, the derivative isn't that large, and so in between these computed points, it can't dip down below 0. The right-hand side, you do the same thing, but it's maybe a more intelligent calculation. You sort of sample the points more sparsely where the thing is large. So somehow this right-hand calculation is maybe a little more efficient. And then the third step is, some kind of local analysis. Like, you just use a second derivative test or something. It's got positive second derivative, so it only has one minimum, and at 1 the gradient vanishes, and so that's it. Okay, so this is the world's worst proof of this trivial fact. But my talk, in a sense, is a kind of, I'd call it like an infeasible calculus problem. It's sort of, in a sense, it's a minimization problem in calculus, but how do you do this problem where it's like if you expanded it out, there'd be kind of billions of terms or something. So let me now get to the subject, energy minimization. So the way it works is that you have some points in the 2-sphere, or for that matter, any metric space. It doesn't really matter, and an interaction between them. So the classic case is you would take 1 over the distance between the points. That's called the electrostatic potential. But there are other possibilities as well. And then you sum over all pairs of points, and that's the potential of the configuration with respect to that energy. Maybe this is called the ground state energy. Anyway, then the question is, given the number of points and the 2-sphere or some other space, and F, which configurations minimize the total potential? So this is, I guess in general, it goes under the heading of Thomson's problem. There was a paper in 1904 by J.J. Thomson, and he really didn't, he considered this on the circle where it's easier. But you could also ask it, later, it just got to be called Thomson's problem, and there's quite a lot of literature on this problem. For about 100 years now or something, people have been thinking about various cases of this. So maybe I'll say something about some popular choices for the potential. 1 over r is the classic Coulomb potential, or maybe the electrostatic potential. Maybe another thing is that people look at power laws. Another thing you look at is you look at minus r to the p, where p is positive. So this is something like the moments. The reason why you take minus is because minimizing minus r to the p is the same as maximizing r to the p. When the exponent is positive, like Polya's problem from around 1950, is you want to know which configurations on the sphere maximize the sum of distances of the points. Another one is the log potential, or sometimes called the harmonic potential. Then there's this funny one, 4 minus r squared to the k, which doesn't look like it's the first thing you would consider, but it turns out to be very nice algebraically. And so what I do, it turns out that this thing is a key potential to look at. Then there's this kind of family of potentials where you look at functions where the function's positive, its first derivative is negative, its second derivative is positive, and so on like that. These are called completely monotone. I guess f of r should be g of r squared, and g has this property. So somehow this is a kind of a natural class of things to consider. So these are some popular choices. I'll give you some history of this. This is again, there's a huge literature, but this is just to give you a feeling for it. So in the beginning, the kinds of results were local results, like which configurations are stable. So in other words, if you like local minima, basically. So there's I took an excerpt, I don't know if it's readable from the back, but I took a little bit from this paper by Harvey Cohn in 1956, and it says that this program was coded in speed code 3 and read in from IBM instruction cards and floating decimal cards for blah, 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 and they could do 150 cards per minute, and then the calculation took less than 2 minutes. So it's pretty slow, but I'm going to take a computational approach to this problem, and if you look at the year, maybe not too long after there were computers investigating energy minimization. Then there was, much later, there's work. So the three kinds of Platonic solids with triangular faces are all minimizers for their number of points and any power law potential. So like the regular tetrahedron, the regular octahedron, and then finally the regular icosahedron. So these are all results from the 90s. And then there's this massive result, which is what I heard about, this result of Cohn and Kumar. I'm not going to tell you what a sharp configuration is. It's a kind of a higher dimensional Platonic solid. It's a kind of a it's an object which has kind of a lot of symmetry as measured by you take a homogeneous polynomial and you average the polynomial over the points versus averaging it over the sphere. And on the one hand, you should sort of get the same answer for all polynomials of, say, degree up to 2m. On the other hand, there aren't that many distances between the points. They're just kind of m kinds of distances. So there's a notion of a sharp configuration. A classic example is the famous E8 cell. This is this kind of 8-dimensional polyhedron, or the Leach cell, which is this 24-dimensional. So anyway, their result, which includes everything else that had been done, is that you have any sharp configuration, and for that number of points on the sphere of the right dimension, that's the minimizer for any completely monotone potential. So they call this universal optimality. So anyway, if you look at this, tetrahedron has 4 points, octahedron has 6, and so what about 5? That's sort of the case. Like, what happens for 5 points? There's no Platonic solid for 5 points, and so so this is this kind of notorious problem. So I'll talk a little bit about what's known. So for n equals 5, this configuration on the top is the triangular bipyramid. It's got a point at the north pole, a point at the south pole, and 3 points on the equator. And this thing is the best, well, for the logarithmic potential, and then for minus r, and then for 1 over r. And what I did was I solved the classic case for for 1 over r and 1 over r squared. I did 1 over r squared just to show that the method was a little bit robust. And then Tumanov showed this for this function g2, which I'm writing it here. It's 4 minus r squared squared. But when you write it out algebraically, it's just like, if you take the two vectors, it's just the two vectors v plus w to the fourth. So somehow this thing is pretty simple. I mean, if you have two vectors, the most natural thing you can do is you can take their dot product. But the dot product changes sign. It can be positive or negative. So if you add 1 to it, or double it and add 2 to it, then it goes between 0 and 4. And so somehow in a sense, this G2 is the simplest thing you could do, or GK. Okay, so then another result is that as you let the power law go to infinity, what Bondarenko, Hardin, and Saf prove is that the minimizer is no longer a triangular bipyramid. It's some pyramid with square base. So this means somehow, unlike these really symmetric things, that in the case of 5 points, there's like a phase transition somehow. Like it starts out with one answer and then it changes as you change the power law. So that's maybe why it's such a hard problem. It's because somehow like there's no kind of general argument in a way where you just say, well, basically any power law is going to work. So this chart on the bottom kind of summarizes what's known. Like, so for these values, for -2 somehow it's not interesting below -2. For -2, any configuration where the center of mass is the origin is a minimizer. So it's sort of only interesting in this range. And so for these values, it's the triangular bipyramid. And then these Melnick, Knopf, and Smith did these careful experiments where they showed that after some value, which is about 15.05, the triangular bipyramid is no longer the best, and it seems to be some pyramid with square base. So there's some phase transition right around a little bit bigger than 15, apparently, numerically. So, okay, well, you probably can't read this. This is the experimental work of Melnick, Knopf, and Smith. They looked at everything up to 16 points, and so for 5, the top row from between 1 and 15.04, etc., it seems to be the triangular bipyramid, and then it changes, and up to 400, it seems to be a pyramid with square base. And then the answer, then they didn't compute after that, but it probably is the same. One more thing to say is that when the exponent is very large, if you have 1 over r to a large power, any small number is going to make this energy huge. And so it comes down, for a very large exponent, you're just trying to maximize the minimum distance. And so this kind of limits to the sphere packing problem. So this is sort of, in a sense, this kind of, the sphere packing problem is a kind of a limit at infinity of this energy problem. Yeah, question?
So you said these were experimental results?
Yes.
So I mean, formally, or what is known? Is it known, for example, that when you take 1 over r to the 100, then a certain configuration is?
No. So that's So the only thing that's known is the result I'm going to present. The only thing that's known is going to be my theorem, right, which I'm going to describe. And my theorem doesn't reach 100. So nothing. I'd say nothing is. I mean, beyond what I'm going to say, nothing is known about this, except in these special cases where they're extremely symmetric, and then quite a bit is known, like any one of these potentials. Okay, so I want to just show you some pictures first. So before I show you the pictures, I have to explain. All you geometers out there will recognize stereographic projection. So this is a map. As I've drawn it, it's a map from the circle onto the line, or the circle minus the minus 1 point. You just pick a point on the circle, and you draw a straight line, and you intersect it with the line through the center of the circle. So this is a map from the circle to the line. You could also do this as a map from the sphere to the plane. And the reason for doing this is that you might want to draw the points on the computer screen. And so you have some points on the sphere, and then you project them onto the plane. Stereographic projection is a beautiful map. I'm probably not the first one to sing its praises. It maps circles on the, if you do it in the two-dimensional case, it maps circles on the sphere to either straight lines or circles. And it maps, the inverse maps circles in the plane to circles on the sphere. So it maps circles to circles. It's angle preserving. It's smooth, even real analytic. It's also great algebraically. It's defined in terms of rational maps. So the whole map is, the map and its inverse are given by just ratios of polynomials. So if you're looking at something like the field of rational functions on a plane and you conjugate it, you get rational functions on the sphere. This algebraic fact turns out to be important in what I do. So anyway, it's a great map. So now I'll show you some pictures. I wrote this program for fun. What you can do is you can fix some number of points, like 10, and then you can animate it. And if you count the points, you'll see that there's 9 points. I'm going to explain this. What's going on? There's 9 points that you see, and there's one additional point at infinity. So always in this program, 1 point is at infinity. And these kind of soap bubble things, you could just think of them as decoration. But what they are is you take the points on the sphere and you take what's called the Voronoi cell. So these are the, each point has a region of points which are closer to it than any other. This gives you a decomposition of the sphere into cells. And then what you're seeing is the stereographic projection of those cells. You can also move different points to infinity. So for example, I've moved a different point to infinity, which reveals that this thing has a kind of fourfold symmetry. So, but you can change the power law to something else. This little caret here is one of these phase transition points noticed by Melnick, Knopf, and Smith. And if you retry it, you're probably going to get something else. You get something with threefold symmetry. Maybe I'll just show you with, with 12 points, it's the classic. That's the icosahedron, whatever. Anyway, that always works. Maybe I'll just show you for 5 points, try to get this to work. For 5, this is one of the views of the triangular bipyramid. It's a little hard to see, but the kind of far away points and the point at infinity make it, they're on the equator, and then the other two make the poles. If you move over to here, or here's another view of the triangular bipyramid. I just moved a different point to infinity. If you go, this caret is at about 15.04. If I go over to here, change the power law, and retry this, it's a pyramid with square base. So anyway, this is really there. I think I have an extra minute, so I just will show you, just for fun. There's one really, so this is, you can do the same thing. This is on a torus. The torus is the product of two circles in R4. And you map the square torus in the plane into the product of two circles in kind of the obvious way, and then you take the Euclidean distance between them. And what's kind of amazing is that this 13-point configuration on the square torus seems to be universally optimal. So sort of for any, it's kind of like a Platonic solid in a sense in the what's called the Clifford torus. Nobody knows how to prove that, but there it is. So this again lets you can choose different numbers of points and see what this thing does. If it looks like it's kind of converging to it for 15 points, you get something almost like a triangular lattice. Anyway, these, if anyone is interested, these are on my website, and you can just play them right on my browser, right on your browser. They're written in JavaScript. Okay, so here's my theorem. So my theorem is basically I rigorously established this, what Melnick, Knopf, and Smith noticed up to for the case of 5 points. So there's a computable number, I called it shin, such that the triangular bipyramid is the unique minimizer with respect to the power law with exponent s, if and only if s is in this interval. So r sub s is, when s is negative, it's minus the moment, and when it's positive. So on the one hand, like this sort of gives an extension of Polya's problem for all the exponents between -2 and 0, and it also shows that the triangular bipyramid is the best up to this constant. Then I also proved that in a slightly smaller interval, the minimizer is a pyramid with square base. I went a little bit further because I wanted to just rigorously show that there was this phase transition. So anyway, and I wrote a monograph about it, and it's on the archive, and that's the monograph. So, and then in answer to this question, this is what's known about energy minimization at all, except for Platonic solids. Okay, so I'm going to sketch the proof of how this works. So there's basically 5 ingredients in the proof, and stereographic projection is the first ingredient. So rather than consider 5 points on the sphere, you can rotate so that one of the points is at infinity, then consider 4 points in the plane. So that's the first thing. Then there's a notion of, well, I'll get to these ideas. There's a kind of a divide and conquer idea, which you have a kind of a moduli space or configuration space of points, and you kind of eliminate most of the space. Well, first you reduce to a compact domain, and then you eliminate most of the compact domain by some explicit kind of computation. And now it has to be extremely efficient to work. This third step is sort of feeds into this divide and conquer algorithm. You want to, you can only do a finite number of calculations, so you have to be able to kind of eliminate whole chunks, solid chunks of the configuration space just from a finite number of calculations. So I'm going to explain about how you do that. Then there's this idea of under approximation, which probably goes back to Hermite, but it's been used by practically everybody in this subject. In a sense, it's the main idea in energy minimization. And then finally, there's this kind of ad hoc trick I found at the end to sort of get the final result. So the plan for the rest of the talk is just to explain these ideas and sketch the proof. Any questions so far? Okay. Okay, so I already explained the map, stereographic projection, and here I'm showing you that, well, on the top you're seeing the two views of the triangular bipyramid. And making a value judgment, one of them I'm considering good and one bad. For reasons I'll explain. Here, FP stands for 4 pyramid with square base, and you can see that this is kind of obviously the good one, and this is where you mistakenly move one of the points of the base to infinity. So this is obviously bad. So the reason why the top one is good is because it looks like this one. So the yellow ones, even though they're different configurations, they sort of share a certain amount of symmetry. And the idea of kind of analyzing this phase transition is sort of lining up the 2 candidate best configurations so that they have as much symmetry as possible in common. And also, when I'm trying to find a minimum in this space, I don't really want to have to deal with both targets. I want to kind of just not deal with this one at all by a kind of symmetry. So I'm going to explain how when I search through the configuration space, I'm going to explain sort of, I mean, this is a technical point, but it's important for what I do. So here, so firstly, if 2 points are very close together, then obviously that configuration is not going to be the minimizer. So when you work out the estimate, at least for the potentials I need to consider, you can arrange so that one of the points is on the x-axis between 0 and 4, and the other points are just in this square of side length 4 centered at the origin. So in the end, what you're considering is a 7-dimensional cube of side length 4. That's your configuration space. And all you have to do to prove the theorem is that for each power law, you just have to eliminate everything but the configurations you like. So I say here, avoid the bad. So this red configuration is supposed to be the same. It's supposed to represent the same configuration on the sphere as the yellow configuration. It's just that I've moved a different point to infinity. So a lot of you are probably familiar with the game Boule, where you have 2 teams and they throw balls at a target, and the winner is the one who has the closest ball. So I'm going to call configuration bad if it's the winner in the Boule. So in other words, I'm only going to consider configurations which maximize the minimum distance to the origin. So in this game, the yellow is the good one and the red is the bad one. And you don't have to compute this. I just proved that if any point is within, say, 1/2 of the origin or something, then it's bad. So I just have to aim for the ones where there's kind of no point close to the origin in what I'm doing. And this is just for technical reasons. Okay, so now I'm going to explain divide and conquer. This is a kind of a computer science idea. So quick, how many points are there in the square? Okay, it's a little bit hard to tell. Okay, well, if you divide the square in quarters, then it's 5 plus 3 plus 3. So somehow what you do in divide and conquer is that you have some problem in a cube, and if there's too much information in the cube to solve the problem, you would divide the cube into pieces that have less information, and you would keep doing this until you could actually understand what's going on. So like if you were really a bird brain and you could only count either 0 or 1, you would kind of subdivide all the way down to the end or something. So this is just a toy for the kind of thing. I'm going to have a 7-dimensional cube, and I'm going to the things I'm going to look at are rectangular solids, and I'm going to look at each rectangular solid, and if there's too much information in it, I'm going to divide it into quarters, and then re-examine it. So I'm going to do the main computational step in my proof is to look at some higher dimensional version of divide and conquer. Okay, so now I want to explain a little bit about nonlinearity estimates. So the thing on the top is just a formula for the second derivative. But really, you should just look at the picture. So here you have a graph of a function where the second derivative is positive and here negative. And the blue is just a graph of the linear function that has the same values at the endpoint. So the main thing I want to say about this is that if the absolute value of the second derivative is small, the function's almost linear. And so it's very near, the black graph is very near the blue graph. So in particular, if you have bounds on the size of the second derivative, then you can get bounds on the max and min of the function just based on the max and min at the endpoint. Plus perhaps, so this is the way my estimates are going to go. I'm going to have some kind of solid cube, some rectangular solid in the 7-dimensional cube, and I'm just going to do some calculations at the vertices, and then I'm going to use bounds on the second derivatives, second partial derivatives of the energy function, and this is going to give me information about the whole thing. So this is how I can kind of eliminate finite, a whole region of space from a finite number of things. Okay, so this is just a cartoon of what I'm going to do. The figure on the left is supposed to be a rectangular solid in 7-dimensional space. It's just this square cross this square cross this square cross this line segment. So the configurations are you pick a point in each of these regions. What you do is you map them to the sphere by inverse stereographic projection. And something really nice happens, because on a square, the 4 vertices are co-circular. And so on the sphere, these 4 vertices are co-circular, and it means that there's a linear, the convex hull of these 4 vertices is just a quadrilateral in space. And so you have these kind of 3 quadrilaterals in one line segment, and then, well, dot product behaves very well with respect to linear spaces, with respect to like pieces of Euclidean planes. And so you can get, the name of the game is to get an estimate for the kind of the minimum energy of any configuration based on what I would call a vertex configuration, which is just your configuration in each one of the squares, it's a vertex. So there's 128 vertex configurations, and if you pretend that the points are on these linear sets, you can get an easy estimate, and then there's some error between the linear set and the actual spherical patch, which is just the curvature of the sphere. It's kind of like quadratic in the radius of the sphere. So the next slide is a kind of a, this is schematic. I'm not going to use power laws. I'm going to use these other ones. And what I'm going to do is I'm going to minimize this thing on the product of Q1, Q0, etc. These are these squares. And what the kind of estimate I'm going to show is that the minimum on the vertex set, the minimum on the whole thing is greater than the minimum on the vertex set minus a readily computable error term, which comes from nonlinearity estimates. And the important thing is that the error term, the bound I get, is rational in the block vertices. And this is really important because I'm going to do this computationally. And when you do things on the computer, you don't want to ever venture into using things like trigonometric functions or exponential functions. You just want to use plus, minus, times, divide. These are the kinds of things that are well set up for getting rigorous bounds. So the idea is that I have a computation which in principle is an integer calculation. You could just do it with integers. But it's a little bit too complicated, and so I do what's called interval arithmetic. But you want rational expressions to feed it to do interval arithmetic. So anyway, this is kind of the schematic. This is what you should remember. Now there's kind of a disgusting slide which shows you what the estimate actually is. There's some crazy kind of interaction term between two of the squares, and these various quantities are this t is like sort of various dot products that are computed from the vertices, and then this delta is something like the distance between the spherical patch and the linear piece, and then this d is the diameter of the spherical patch. And you just get this crazy formula, and then you sum over all pairs of quadrilaterals, and that's your error term. And then my theorem is that the minimum in the solid is greater than the minimum from the vertices minus the error term. So anyway, this is written down in the book. I just wanted to put it there just so you see that there's sort of an actual formula. And this, in a sense, is the most important part of the whole proof, because you're doing this calculation, the divide and conquer calculation, in 7 dimensions, and it's very unforgiving. If you don't have a good error term, the calculation will never finish, in a sense. So somehow this is a pretty sharp error term for this kind of thing. So most of the work was kind of getting a good error term so that the computer would actually run. Okay, so briefly, I call this kind of the marriage of these two ideas. You have one of these rectangular solids, which is always, like maybe it's this one cross this one cross this one cross this one, and then you divide it into 4 by taking one of the squares and dividing them into 4, or taking this segment and dividing it in half. So this is the kind of subdivision that you do, and then you apply the energy estimate. So what my now I'll bring this up. So what you're looking at over here is sort of a computer version of the picture as I've been showing you. You can let's hope that. Okay, so you can sort of move these things around, and this window over here, it's giving it a. Well, I'm a professor, so I made a grader for the configuration. So, like, here's an example. So the target energy for the triangular bipyramid is, I think it's 51. And when it computes the minimum vertex energy, it's like 52. And then it's got, the error term was a sum over a bunch of pieces. And I break the sum up into 4 pieces, which based on the contribution of each square. These 4 terms, I just break up the sum, and they say how much each square contributes to the error. So like the orange square contributes like 2.53, and then et cetera. And then when I subtract everything, I get 45, which is less than 51. So based on my energy theorem, I cannot tell that the minimizer is not there. But if I subdivide it, I subdivide the one that has the biggest contribution to the error, and now I'm at 48. I'm getting there, and I subdivide again. There's 4 choices. I'm just picking one at random. So I keep subdividing it, and then finally, the error terms are small enough so that this thing, my theorem tells me that every configuration in here, none of them can be a minimizer. They're all greater than the triangular bipyramid. And I'm not using a power law. I'm using the function g3. So my algorithm is I start with the whole space, And well, first of all, if you look carefully at this, you'll notice that 2 of the points are in the upper half plane and 1 is below, and 1's on the x-axis. So if I had a configuration where 2 were in the lower half plane, I could always reflect it. So there's some symmetry I can use to avoid excessive calculation. And also, if one of them is too close to the origin, I can say it's bad and just eliminate it. So I don't have to consider every configuration. I can use symmetry to sort of eliminate stuff. So this is the energy G3, and the calculation, and there's one other way it eliminates it. It also eliminates a configuration if it's within like 2 to the minus 15 of the triangular bipyramid, which is the vertices of that navy diamond. So so this thing runs, and if it halts, if it runs to completion, it's a proof. Let me just run it and talk. So now it's kind of eliminating junk. I have to just blather on for about 2 minutes before it does something interesting. If it actually runs to completion, and it's let me get rid of this. This slows it down. And the calculations are exact, then it constitutes a proof that any minimizer for this particular law has to be within 2 to the minus 15 of the triangular bipyramid. Everything else is eliminated. This is doing floating point calculations. So it's not, there's errors in the calculation. So what you do, the way interval arithmetic works is that you have some expression, like you want to add 2 numbers. So you take your 2 numbers and you find intervals with rational endpoints that contain them. And not just rational endpoints, but dyadic rational endpoints that are represented by the computer. And then the computer is guaranteed when it adds such dyadic rationals, it will find the dyadic rational that it can represent that's closest to the true answer. So you take your 2 intervals, you add the endpoints, take the max and min, and then you round outward 1 click, and then you get a new rational interval, and there's a guarantee that the true answer is in that interval. So you can do this for times, minus, divide, and plus minus times divide, as long as you're not dividing by 0. And so you can do this for any rational expression. This is how you rigorously do computations on the computer. So this thing runs. I want to let it run a little longer. It's finally going to settle down. Now it's starting to do some real work. Now it's no longer eliminating junk. It's actually eliminating stuff that's very near. The picture is that you have this little neighborhood, like 2 to the minus 15 neighborhood of the triangular bipyramid, and there's all the stuff which is kind of just clustering around the boundary of this neighborhood. That's where like all this stuff is. So it looks like the computer program just died, but actually you can zoom in and see that it's still working. And so you can go to you can go around and you can see that yeah, it's actually still alive. But this is sort of an indication that this computation has to be extremely efficient, because if you divided the space evenly, you would never get through it. Okay, so now it's I guess it's coming out of it again. So it goes, and if you let it run for about 15 minutes, well, this is just floating point, but it stops after about 15 minutes, and if you let it run for about an hour and a half with interval arithmetic, it stops. Okay, so what I can do with this is I want to open this up and go back to something here. Alexander Tumanov made this great observation. He proved it. He proved the result for G2, but he said if you could also prove it for G3, G4, and G5, then you could actually also prove the result. It implies the result for all the power laws between minus 2 and 2. So I'm going to explain how Tumanov's observation works. And so that means if I want to get all the power laws between minus 2 and 2, I just have to do G3, G4, and G5. So I just showed you I can run this for G3 and G4 and G5, and all this takes about like under 10 hours. And so I can actually prove it for these things. So by Tumanov's observation, I get everything from minus 2 to 2. So I want to talk about how this works. And this is this idea of under-approximation, which is the main idea in energy minimization. Okay, so I'm taking a function f of r equals 1 over r to the s, and these values, root 2, root 3, and root 4, which is 2, they're the distances that actually appear in the triangular bipyramid. So 2 is the distance from the north and south pole. Root 2 is the distance from a pole to an equator point, and root 3 is the distance between the equator points. And so here I'm looking at, that's not good. Okay, well, the G1 is a very simple one, and you can show easily that the triangular bipyramid is the best. So what I do is I take a constant, I take this linear combination of 5 terms, and what I'm interested in is finding a linear combination with positive coefficients which is smaller than the power law but agrees with the power law at these values. So let me just explain that you can get started on this problem because you have 5 unknowns, and at root 2 you want to match the value and the derivative, and at root 3 you want to match the value and the derivative, and at root 4 just the value. You don't care out here because these aren't distances that occur on the sphere. So this is 2 constraints plus 2 plus 1. You have 5 constraints, 5 unknowns. They're linear constraints, so you can just solve for these coefficients in linear algebra. For each exponent you would get these coefficients. And what you hope is that they're positive and that the resulting linear combination is an under-approximation. So let me just say, suppose you could do that. What Tumanov observed is that you can do it at least when the exponent is between minus 2 and 2. So let me explain what this gets you. So now I'm going to prove that for any function where you have this under-approximation, the triangular bipyramid is the best. So this is the only calculation in the talk. X is some configuration, and T is the triangular bipyramid. And F is this weird, F is the power law, H is this weird combination. So F of X is greater than or equal to H of X. Why? Because H is an under-approximation. And then H of X, just by definition, is this linear combination. But then all this for X is bigger than all this for T because I've already proved it, the result for these G's, and the coefficients are positive. So you just have, these are all bigger than these, and you're taking positive an average. So this is bigger than this, and then this is just equal to H of T by definition, but H equals F because H and F agree on all the distances that actually arise in the triangular bipyramid. So these great results of Koenig-Kumar, the reason why they work is because you have these highly symmetric configurations where there aren't that many distances involved. And so you're trying to under-approximate some kind of function, and you don't really have that many points you have to hit. On the other hand, you have like all this agreement on homogeneous polynomials, and so you have sort of a lot of functions you can use in place of the G's to make this work. So this is sort of a really vague sketch of this big result of Koenig-Kumar. Okay, so anyway, if you have all this, you get the result. So here's a picture on the top. What I'm showing you is these different curves are the value of the coefficients. And if I use G1, G2, G3, and G5, all the coefficients are positive until about 2.5. So my calculation, once you get in a little tiny neighborhood, then you just use something like local analysis, like you show that the Hessian of the energy is positive definite. So my calculation plus some local analysis proves it for G1 up to G5, and then when I just look at the coefficients, I get up to exponent 2.5. Well, then I decided to do some cooking on my own, and if you use G1, G2, G4, and G6, you get up to exponent a little bit bigger than 6. The triangular bipyramid doesn't minimize G7 or G8, so your luck kind of runs out. But then I got the idea to look at G1, G2, G5, G10 plus 28, G5 plus 102, G2. So the idea is that the triangular bipyramid is a minimizer for these and not for this one. But if you add a bunch of these back, you can add enough so that it's, again, a minimizer. And when you do this, you pick up all the exponents between 3 and 13. So this is getting closer to the cutoff of 15. This is never going to work because, you know, you're never going to sort of find there's some inefficiency in this. And whatever combination you take, you know, you're never going to be able to get an exact value. So let me now explain the proof. I use these kind of magic functions to get up to 2, these to get up to 6, these to get up to 13, and then I try to use this one to get up to something a little bit larger than the phase transition, but it won't work. The triangular bipyramid is not the minimizer for this. So, I mean, if the triangular bipyramid really was the minimizer for this, then I would prove a false result. I'd prove that the triangular bipyramid was best up to something beyond the phase transition. So there seems to be no way to find some magic combination which exactly works up to the phase transition. But what I do is I just run the program anyway. So the idea is that I just run the program using this thing, and I just note the failures. And what I notice is that there are these little regions, and unless you put 1 point here, 1 point here, 1 point here, and 1 point here, you have higher energy than the triangular bipyramid. So using this last function, I eliminate everything except for configurations in here and exponent in between 13 and 15.05. So then there's one more idea in the proof. The final idea is a symmetrization argument. So the yellow and orange points, that's my original configuration, and I'm going to replace it by a new configuration that has fourfold symmetry. So the procedure is I first rotate the yellow configuration so that these 2 points have the same height, the same y coordinate. And then I look at the horizontal distance between them, and I put the blue points on the x-axis symmetrically placed so as to have the same horizontal distance. And then I do the same thing for the vertical direction. The distance between these two blue points is the same as the vertical distance between these yellow points, and they're evenly placed. So I have this small 7-dimensional set, and I have this linear retraction onto the set of configurations with fourfold symmetry. And then my next theorem is that this decreases the energy for the leftovers. And so all you're left considering is just configurations with fourfold symmetry, of which both the triangular bipyramid and the pyramid with square base are examples. So I just want to say a word about this argument and why it works, why it's possible to do this. So when you compute the energy of a 5-point configuration, you have these 10 terms. And then you're doing this symmetrization operation, and these 10 terms are changing. And how are you going to estimate that this goes down? And also, how did I find this operation? Basically, I tried all possibilities. I tried like mapping them back to the sphere and averaging on the sphere. I tried rotating. I tried reflecting and averaging. Anyway, this one was like method number 7, and it worked. And it's so good that here's a kind of picture of the 10 different bonds, and they kind of break up into a sum of 3 plus 3 plus 3, 4 plus 3 plus 3. And this symmetrization operation, at least in this little range, it's so good that it actually it decreases each of the sums separately. So now I just really have a geometric problem involving triangles and quadrilaterals, and this is much easier to solve. The way it's solved is you can write at least for there's a certain I won't say too much about this, but there's a certain, like here for the 4 points, you originally have 4 distances, and after you symmetrize you only have 1 distance. And it turns out that just by the way LP inequalities work, if you can prove this for one exponent, you can prove it for all the exponents. So I just really proved this, in this case, for example, for exponent 2. And you just write the energy down, the energy before and after. It's some enormous polynomial. And the proof involves showing that like a polynomial in 5 variables and like 300 terms and degree 40 is positive on the unit cube. And there's, I kind of invented some kind of positivity test for this. And there's many in the literature. But I used my own kind of positivity certificate. You have these enormous polynomials, and you just check algebraically that they're positive on the unit cube. So anyway, it's an algebraic calculation. I'm almost done. This symmetrization, it reduces you to just considering the whole picture in a 2-dimensional set for these remaining configurations. And then I found some other symmetrization that just reduces you to a 1-dimensional set, which just is the pyramids with square base, and union one extra point, which is just the triangular bipyramid. So then it's just a calculus problem. In the end, what you get is you get these 2 minima, one for the best pyramid with square base and one for the triangular bipyramid. And I show that like in this little range, as you change the exponent, one of the values goes up and the other one goes down monotonically. So there's this unique place where they coincide, and then they go off, and then the triangular bipyramid is better. So anyway, that's it. Maybe that's the proof. I just want to say one word about this. I guess I tell students this is not a good way to do mathematics. I mean, the problem is it answered the question, but it only answered this question. The other thing about it is that I think it's probably hard to check. Say it's hard to have a refereeable account of this. Although that's only because of the culture and not because of the difficulty. I mean, a programmer could reproduce all the programs. They're not complicated. So one problem is that I'm not sure how this is going to be refereed, and I guess I just think of it as a time capsule. Like either there's a rising tide of technology in this subject, and eventually, in a couple years, maybe it will answer this question in a more satisfactory way, or it'll be another 50 years, and then people, computers will have developed, and this will be a more standard kind of approach. So I just think of it as like, well, I don't know if anyone's going to read this now, but there it is. Okay. Okay, so, yeah, question?
What happens with the symmetrization technique globally?
It doesn't work. Yeah, if you move, I mean, it's fairly robust. Like, I mean, what I mean is I had this tiny neighborhood that I was interested in. If you maybe you can enlarge the neighborhood by a factor of 5, and it still works. Although I wasn't able to prove that. I mean, my proof is very delicate, but yeah, but then if the points are sufficiently far away, it definitely fails. Yeah, so that was like kind of logically I had to eliminate almost everything before I could use this symmetrization argument. I mean, I'm hoping, I want to show that like you get a triangular, I'd like to show that after this phase transition you always get a pyramid with square base, and I think that this symmetrization should do it eventually. Yeah. All right. Well, thanks for listening.